Well, greetings, tube fans. This is the second video for the Selectron, the SB-256 memory tube. In this presentation, I'm going to go over the selection process. How do I address one of 256 bits? I'm going to offer a very quick and dirty nuts and bolts explanation how this is done, and then go into a more in-depth physics explanation with potential maps and that sort of thing. You can certainly skip over that if that does interest you. I will then go through the decoding process. That is, how do I address one of 256 bits? And it's really kind of clever how this tube is put together. Finally, I'm going to go over a circuit that would allow me to drive these selection bars either to 0 or minus 250 volts with just simple TTL signals. My microprocessor is going to control this, so I need a driver circuit which will switch between 0 and minus 250 for each bar. So let's get started. So we want to describe how I can deselect all islets except for the one I'm interested in. We need to do this in the read or write process. Now recall, in the idle state of the tube, I need all of the selection bars at 0 volts. That allows this maintaining current to come through. The islets need it to maintain their stored potentials. I'll cover that in video 3. Now I'm going to turn this around to kind of cue you up for the next image I'm going to show you. We have our cathodes right here, or emitting current. We have our vertical selection bars, horizontal selection bars, and then I'm going to look at it like this. So the short answer in how I deselect islets is I bias the windows, if you will. You notice that the vertical selection bars in this image basically form a window for electrons to come through. So this particular window is open since these two are at 0 volts. On the other hand, this window is shut since this is at minus 250 volts, even though this is at 0 volts. The current coming off of this cathode can't get through. Now, I would like to explain with in further detail with a little bit of physics, is this 250 volts sufficient to keep current coming through, even though one side's at ground? Turns out it's more than enough, but I'd like to show you that anyway. So the last image I want to leave you with is this guy, and it's from the technical report, the RCA review. This top image is very similar to the thing I just showed you. Anything that shows positive like this is actually 0 volts. Anything else is minus 250 volts. So this is sort of our two-dimensional view from the point of view of the islets or the cathodes. Current is coming in and out of the page. And again, in the quiescent state of the tube, all of these bars will be at 0 volts. But when I'm reading or writing, I need to selectively open a window. And in this example, this guy is open since all 4 bars that are surrounding this window are at 0 volts. All others, mostly, are at minus 250 volts. So even though this window here, only has 1 bar at minus 250 volts, that's sufficient to keep current from going through this window. And in a moment, I'd like to kind of go through the physics of how that's enough. The other thing you might notice is, in addition to the 4 bars that I've got from my window, I've got a couple other here that are biased at 0 volts as well. And that has to do with the internal structure and how these guys are wired up. And it's actually very clever. It's part of the decoding scheme for this tube. Now, to come back to the physics of how this operates, what I'm going to do is start with a very simple diagram without the selection bars, and we'll add them in. So let's start with a simple arrangement. I have my cathode here, collector here, biased at 0 volts and 180 volts respectively. And what I want to do is sort of develop the background for what I'm ultimately going to do, and that is I want to do a 2D simulation of the potentials in the space between these, and once I add my selector bars. But I'm going to introduce a little bit of stuff here first so it justifies what I do later on. We're going to assume our cathode emits our electrons. They're thermionically emitted. They're emitted with very little kinetic energy. They're kind of just dribbling out of there. Let's just put an arbitrary charge, and we use the letter Q for charge. And we already know that if this potential is higher than this, we're going to have an electric field that goes back to the left. And in physics, we tend to look at things in terms of forces and fields. So in this situation, we have the force on this charge Q is the property of the charge Q times the electric field. Now, the electric field is very real. It's there. But what we observe physically are forces through accelerations of the particle. We have a similar force field equation in gravitation. Let's just write this down here. This is the gravitational force on a mass in a gravitational field G. It looks very similar. Notice that both of these look like property of an object, that is, what property talks to the field that it finds itself in, so property in a field. In electrostatics, or really even in gravitation, we can write fields in terms of the gradient of some scalar potential. Now, I know that sounds fancy, but really all this just means directional slope. This is just a scalar size. It's just a map of numbers, if you will. So as an example, I want to apply this to our situation right here. E in the x direction, this basically says I want the slope, that is the change in potential over position. So I need to mark a couple of positions first. So this says we're going to take minus the change in potentials, and I'm just going to write potential at B minus potential at A, and then of course I've got to divide by, since this is a slope and this is slope in spatial coordinates, this is their x direction, we're going to say x at B minus x at A. Now we always write this should smell a lot like change in volts over change in position. The minus sign here, if the potential at B is higher than it is at A, I'll end up with a minus sign, and that just means the E points in the minus x direction. And indeed, that's what we have here. The potential at B is greater than that at A. The only thing that matters in physics are differences. So if I added a constant scalar to the potential map, it really doesn't change anything. The only thing that matters are changes in volts, potentials per change in distance. Continuing on, I want to stick this into here. We're going to say force equals, just and rearrange a couple of things, the gradient of Q times my potential. What I want to do is get a map of Q times the potential. This has a special meaning, and I'll tell you what that is in just a moment. But that's the goal. We want a two-dimensional map of Q times the potential. This is going to look just like a topographical map for a hiker. Now, the Q in here, of course, in our application is the charge of an electron, and I'll stick that in just a minute. But I kind of want to go to a gravitational analogy and kind of show you the direction I'm going with this. So bear with me for a minute. Let's change over to a gravitational analogy. In gravity, we're going to start with a little particle here. He has mass m, and we're going to put him in a gravitational field that points down. So we know that the force on our little particle is m times g. Since m is positive, it always is in gravitation, both of these point in the same direction. And I'll go ahead and draw the force kind of a little off to the side, but it's aligned with the particle. Now, what I want to do is move this and start talking about something called potential energy. The change in potential energy we can define potential energies as minus the work done by this conservative force. This only works for conservative forces. Gravitation is certainly a conservative force. That just means if I move this thing and I kind of bring it back to the same point, the work done will be, net work done is zero. Said another way, there's no friction, there's nothing else taking energy out of the system. So work done, basically, I'm going to integrate the force, which is mg, dotted with some direction I'm going. So let's draw the direction. I'm going from an initial position to a final position. Notice I'm going up here. Now, this has special meaning. It's a dot product, but basically what I'm going to do is take the magnitude of the force, mg, times cosine of the angle between the force and my displacement. That angle, 180 degrees, and then when I do the dot product, it's magnitude times cosine of 180. Essentially what that does is give me another minus sign, and ultimately I can write potential energy, or change in potential energy, is mg, and I'm just going to write change in elevation. Now let's go back to our electrostatic case. We have a similar picture. Instead of mass m, we have charge q, and we have our electric field. And for the moment, I'm going to pretend like he's a positive charge. So force points that direction. And we're going to do the same thing. I want to move this over to the right. I'll call that direction X. I'm going from initial position to final position. And I want to define the change of potential energy. Well, when I go through this all over again, the math is virtually identical, and I end up with change in potential energy equals Q, electric field, change in position. Notice that both of these potential energies look like a property, mass or Q, a field, G or E, and a displacement. Now, why am I doing this? The potential energy, if I know how potential energy looks in all areas of space that my charge might be in, I can instantly tell what it's going to do. Is it going to go down a hill? Is it going to go up a hill, or whatever? So let's do a roller coaster, just sort of as an example of what I mean. So we have a roller coaster. We have riders that start way up high, and we're just going to give them a nudge just to get over this little hill, just barely kicking them out. And we're going to let them go down this hill, and we want to see what's going on down at the bottom of the hill. If I apply the idea of conservation of energy, conservation just means energy is not created or destroyed. Said another way, whatever total energy I have at the top has to be the same as at the bottom. So I can write it like that. So I've just got to identify all the energies I have at the top and then at the bottom. At the top, I'm going to state that we have zero kinetic energy. We're just barely starting from rest. And I need gravitational potential energy in here somewhere. Now, this says change in potential energy is this. That means I need to pick a reference. Where is zero going to be? I can pick that anywhere I want, but I'm going to pick it up here. I'm going to say my initial kinetic energy and potential energies are zero. So when I plug in energies, I've got 0 plus 0. That goes here. Now, at the bottom of the hill, this says change in potential energies, mg, change in h. Or rather, change in y, where I'm going to put an h in for this change in y. And since I'm going down, this potential energy is negative. And of course, in the final state, I will have some kinetic energy. It's not zero, so I'm just going to leave it like that. So my final energy looks like minus mgh plus kinetic energy. Solve for kinetic energy, positive mgh. Now, the point of this is just to say, I'm going to have some positive kinetic energy. Yeah, we could solve for velocity from this if we wanted to, but I want to look at this blue curve as a curve in space. I want to just define it at like maybe a function on a graph or something. And I instantly know as I go down this curve, it's going to be accelerating down. It's going to feel a force because of the slope of this curve. That's how I'm going to read it. We can apply our electrostatics to this case. And I'm going to do this. I'm just going to pretend, okay, we've got an electron up here. We're going to let our electron go down this roller coaster, and we're going to make a couple of subtle changes to make it applicable to what we're dealing with. Now, to do this, what I'm going to do from the previous picture that we had, E times the change in position is really just change in volts. This is always true for any situation. This is true only for uniform electric fields. But we're going to use this form of it since in my electrostatic example, I know what the potentials are. The potentials, let's mark those in blue. 0 volts plus 180 volts. We're now ready to apply conservation of energy to our electrons. So I'm going to start up here. I've got 0 kinetic energy, and indeed, if I plug in 0 times charge, I have 0 potential energy, just like I did before. So I will write 0 plus 0 equals, now E final. This says Q, and change in volts. I'm going from 0 to positive 180, and then I've got plus kinetic energy. At this point, I need to substitute the actual charge of the Q here. I've been using Q as a generic placeholder. I'm going to replace it with minus E, and here's 180 volts plus kinetic energy. The E is the magnitude of the electron charge. It's fixed. It's 1.6 times 10 to the minus 19 coulombs. But when I move this around and solve for kinetic energy, notice that I put the E after this, and then I kind of packed it in with the volts. So what I end up with are energy units that look like or are electron volts, and that's perfectly acceptable. The curve, potential energy curve, it is volts times charge. This is a positive 180 volts for the electron. That's a lower potential. The nice thing about potential energy curves, you can instantly tell if something's going to work or not. So I'm going to draw another roller coaster, but I'm going to add something to it. So I've added a hill to our roller coaster. And remember, our little carts have very little kinetic energy, and they're starting where I'm calling 0 potential energy. And I put this hill here. We can see that instantly they're not going to go up this hill. They're going to be very disappointed, these roller coaster riders. So that's the idea in our selection process of the tube. We're just going to make the potential energy curve in the region between cathode and collector. We're just going to raise this up. Now, from the point of view of the electron, let's make this our electron now. This was 0 volts. This was positive 180 volts, and it's a lower potential compared to this. So that means this, being a positive potential energy, would have to be a negative potential. For example, a negative potential, if I kind of consider this to scale, maybe 50 volts. That means that the potential energy for the electron will be positive 50 eV. This also says if I wanted my electron to go over this hill, I would have to give it a kinetic energy of at least 50 eV in order for this to happen. But again, they're thermionically emitted. They have very little starting kinetic energy, so they're not going to go up this. So let's return to this. The idea is I need a 2D map of Q times phi, or this is just potential energy. This is Q times change in volts. So that's what we're going to do. We're going to develop a 2-dimensional map of the potential energy. To get there, what we have to do, first of all, in free space, we know that the divergence of the electric field is 0. This implies the following. This is Poisson's equation. At least for me, that's difficult to pronounce, but it's a second order spatial differential equation. We're not actually going to solve this mathematically. What we're going to do is make the space in this region all around it discrete. That means we're going to model it with a spreadsheet. This means for a certain point in space, we're going to let our spreadsheet values represent the potential at that point. So we're going to have a full array of all these potentials. That'll be my map. So it turns out in the discrete form of this guy right here, I can actually solve for the potential at this point by taking the average of the neighbors. This just means we're going to take the average of the nearest neighbors, these cells around it. Take that average, put it in there, and then what we're going to do is move over to the next cell and do the same computation. Yes, this is going to be a huge circular reference issue, but that'll be okay. So one thing that we need to add to this are the selection bars. I didn't draw those in yet. So we're going to draw in our selection bars kind of like this. These would be as drawn, these are the vertical selection bars. So what I do in my spreadsheet, this is the formula I use for all free space, but I'm going to hard code the actual potentials wherever my electrodes are. So we want to investigate what happens to our electrons, what potentials do they see if our selector bars are at 0 volts or if they're at minus 250 volts. So let's go to the spreadsheet and see how we do this. So here we have our spreadsheet. It's just a collection of cells. Ignore the values that's in there now. It's just left over from the last time I used it. So I'm just going to sort of pick a cell and show you that all I'm doing is averaging the numbers around it. So let's go to formulas and trace dependence. I'm referencing each cell around it, and it really is just an average. That's true for any cell I pick. Let's remove arrows. The only issue is I've got a finite array here. We have to be kind of creative at the boundaries, and really all I do for this is reference the cells above and below and the one that's inside my grid twice, since I don't have a value over here. This will be approximate for an edge, but that's okay. We're just trying to get a nice feel for what's happening here. So the other thing I have to do is draw my electrodes kind of to scale. So I'm going to skip over to the technical diagram. This is the dimensions of all the little bits and bobs in the tube. I take the dimensions off of this. I'm just using the vertical selection bars here and here. This is our cathode. I'm going to ignore the horizontal selection bar. I just want to see what happens when I bias these vertical bars at 250 or 0, whatever. And then of course we have our collector plate. So those are the only components I'm going to draw. But I take these dimensions and I scale this to my spreadsheet. So I think what I chose was a cell represented 0.01 inches. And I've kind of sketched or outlined where these electrodes are going to be, but what I need to do is hard code what those numbers are going to be. So let's make this one 250 and let's make this one 0. First thing I'm going to do is just sort of highlight it so I can see what I'm doing, and then I'm just going to hard code and make this minus 250. Similarly, I'm going to make this one all zeros. So we have our selector bars at minus 250 and 0. We have our cathode here. This is also going to be 0. Then our collector plate. There's a small hole in it. This needs to be 180. So now we have a spreadsheet where free space, what I do is I calculate the potential at some point by averaging the cells around it. I have electrodes where I have hard-coded the potentials, and then all I have to do is hit recalculate F9 and Excel, even though it's, and I did have to turn off circular references error, but it will, I'm just recalculating, hitting F9 a couple of times. It converges fairly quickly. Now I'm going to show you a map in just a minute, but read these values as volts, multiply them by minus E, and you'll have potential energies. So essentially, an electron starting, whoa, that is, I forgot to change that. Let's make that one a 0. And let's hit F9 again. The electrons are starting from the cathode at 0 volts, and everywhere around it, it sees essentially negative potentials. This is a huge negative potential. It's reaching across. It's if you will, I'll show you the map. It looks like it's stretching space a little bit. It's going to look like a rubber sheet. But just looking at these values, I can instantly tell that an electron trying to leave this at 0 volts with 0 kinetic energy is not going to get over this potential. It's a positive potential owing to the fact that the electron is negative. But let's throw this into a grapher and kind of show you what we're talking about. So this is actually the same simulation with both selector bars at 0 volts. And you can see that the electrons have a clear downhill path, if you will, to the collector. So it's going from cathode to collector. They're going to accelerate down this hill. I mean, just imagine putting a ball bearing on this thing. This is 0 volts. This is positive 180 volts. And again, this is a lower potential energy because of the charge of the electron. Now, going back to our other case, this is minus 250 volts. It's a positive potential energy now for the electron. And we saw just by looking at the pure values that the region around our cathode is all positive potentials. There's no way an electron is going to escape that little potential well. So this is how we're going to turn off current to a particular eyelet or storage bit. So right behind where I have the collector plate, this is where the eyelet or storage bits are going to be. So in this case, I have just one bar of the window at minus 250 volts, and that's sufficient to keep electrons, current, from reaching this eyelet. On the other hand, if I'm selecting this eyelet, all bars around the eyelet must be at 0 volts. So here we're going to start talking about addressing the individual bits of this tube. This is another diagram from that technical report. It shows how all of the selection bars are interconnected inside of the tube. There are 4 64-bit blocks, if you will, 2 and 2 on each side of the tube. Now, the first thing I want to point out is that there are 4 groups or groupings of bars. There are the H group, H1, 2, 3, and 4, horizontal group. There's also the H prime group, 1 through 8. So these are 2 different groups of bars. They're all horizontal. Then we have the vertical prime, V1 and V2, and then we have the unprimed vertical, 1, 2, 3, and 4. So remember, in the idle state of the tube, the quiescent state of the tube, all bars must be at 0 volts. But when I am trying to select a bit, what I need to do is make one and only one bar of each group 0 volts, and then all others of those groups are at minus 250 volts. So now we're ready to discuss how we make this selection. These squares right here are just sort of symbols. They're essentially decoders. So what we're going to do is take an 8-bit binary address and decode this. And if you want to think of these 2 squares right here, they are essentially a 2-line to 4-line decoder. In today's modern digital electronics, CT electronics, these would be equivalent to a 74 LS 139, a 2-bit to 4-line decoder. And then this guy right here, 3 bits, 8-line decoder. Now, this is an 8-bit address. Each address, the way this is drawn, and the way it was originally implemented, we had a Q and a not Q for each bit. We don't need to do that. We're just going to call this our least significant bit. We're going to call that A0. So that's our least significant bit. The next one over, I'm going to call that address bit 1, and then so forth. So let's pick a random digital number for an address and see where that leads us. So we're going to do 0, 1, 1 for that, 1, 1, 0, 1, 0. Let's do that. So the way I do this is we're going to decode each little bit and then highlight the bar that will be at 0 volts. So with the least significant 2 bits right here, this decodes to a 2. Also keep in mind, this was originally drawn starting from numbering from 1, and in today's digital vernacular, we start from 0. So this is a 2, so I'm going to start counting 0, 1, 2. So I need to make this bar 0 volts. And what I'm going to do is highlight this bar. I'm going to draw it in green just to show that this one is at 0 volts. Now, really, I should continue these lines into each matrix, but I'm trying not to clutter up the diagram too much. So the next thing, I'm going to decode my next most significant bit. This is A2. This is a 1. So I count from 0 to 1. I need to highlight this one. And again, I really should extend these all the way up, but I'm trying not to clutter this diagram. Now, when I make these bars, these selected bars 0, all others need to be at minus 250 volts. I'll just sort of mark these in yellow when I've selected one and only one of each group to be 0 volts. All others of that group have to be minus 250. Continuing on, these next 2 bits, A3, A4, this decodes to a 3. So I'm going to count 0, 1, 2, 3. So I need to make that one 0 volts. Now I went ahead and drew this one all the way in because this one is unique. There's no other interconnection inside of the tube. So I'm going to go ahead and do that one. And then again, keep in mind that all others going in are at minus 250 volts. So one and only one from each group. And then finally, this decodes to a digital 2. So I'm going to count 0, 1, 2. So I need to make this one green. All others will be yellow. I'll probably skip that. And then I'm going to start extending these into the grid. Now, again, I'm trying not to clutter this diagram too much, but what I'm looking for is a window that has all 4 bars at 0 volts. And I see if I extended this one, there would be no other horizontal bar that would be at 0 volts because this one is at minus 250. So I see that this one and this one adjacent to each other, these are at 0 volts. So I know these 2 are the ones I need to be looking at. And then again, I've got one vertical bar coming up here, and the one adjacent to it is also at ground. And yes, again, this one is also at ground, but there's no other bar next to it that's at ground. So we're not going to select any of those bits. So it looks like we have selected this bit right here with this 8-bit address. Again, keep in mind that all of these other bars are at minus 250 volts. That means any window that has at least one at minus 250 volts will not be selected. So this is how we do the selection. So I need to add a couple more pieces of logic to this to actually implement this. When we build a circuit, these guys right here really are just going to be these 2 integrated circuits. It's simple as that. But I need to add some gating on this so that whenever I want to be in the idle state, everything is 0 volts. So what I'm going to do is basically add an AND gate to every line, every single one of them. There's a bunch of bars here. I didn't draw that so well. AND gate. So every one of these guys are connected together, and I'm just going to call this my Q state. So if this line is low, everything else is going to be at 0 volts. It doesn't matter what my selected decoded thing is. If the quiescent state line here is 0, my outputs are all going to be 0. On the other hand, if I make Q state 1 or a high, then that would allow the decoded address to come through, and we've got our selected bits. Now I've got one more thing, one more bit of addressing or selection to do here. If we are trying to write a low, a 0, during the write process, I have to turn off the selected bit as well sometime during the write pulse. So I need one more bit of logic that will actually deselect this one as well as everything else. So I need somehow to not select during this process. And essentially, all I'm going to do is look at the enable pins on these decoders. That's really all we're gonna do to this is look at the enable pin, and I will use the enable pin to deselect everything. So we basically have 3 different logic states for this tube. We have the idle state, in which all bars are 0. This logic state needs to take priority over everything else, and if I use AND gates in the way I suggest, that will happen. I need to be able to select 1 bit based on this address. Then I need to be able to deselect that bit as well. So in other words, not select, that means all bars are at minus 250. And this will be important during the write process. Now what I'd like to do is kind of look at one of these 64-bit blocks in a bit more detail and kind of show you again. I am selecting one of each group. Here I'm selecting H2, V1 prime, V3, H2. All other bars other than the selected one are at minus 250. The selected ones are at 0 volts. So with what I've got going here, I've selected this bit. And as long as 1 bar is at minus 250, I will not get current through this window. What I'd like to show you next is what happens when I increment the address. If I just start counting the 8-bit address, what happens to the selected window? It doesn't go through in an order that you might expect. So I'd like to show that to you next. So I am showing you a 64-bit block as I increment the address count from 0 up. And I have the address of the selected bit shown in decimal and binary form. And we're just incrementing. We're going from 0 to 63. And you can see that the selected window kind of jumps around a little bit. That's just due to the nature of the way this thing's wired up. But it does eventually hit all 64 bits. So how did we do in the actual implementation of the tube? Well, you can see in the video here as my microprocessor increments the address count, and we're just looking at this lower 64-bit block. The address bit does seem to jump around a little like the animation, but not quite in the same order. And I kind of feel like this is an error in the data sheet. Some of the horizontal and vertical selection bars may be out of order or something to that effect. But I'm happy with the fact that it actually goes through all 64 bits at a time, 1 panel at a time. So we're just going to leave it like this. So I'd like to go over the selector bar driver. The purpose of this circuit is to drive my selector bar between 0 and minus 250 volts, controlled with a digital input. I basically have a simple MOSFET switch going on here. This is a high voltage MOSFET. I'm using a VP2450 for this, although for the simulation I'm using a different transistor. Whenever I have a digital in of a low or a 0, the bar voltage will end up being near ground. Digital high going into this, the bar voltage will be at minus 250 volts. I did choose to optically isolate the digital side from the high voltage side, although it turns out I didn't really need to do that, but this was useful anyway. So this is the simulation of the circuit. The green curve digital in, whenever I have a high, the bar voltage is near minus 250. Whenever I have a digital in of a 0, the bar voltage is near ground. The blue curve is the potential at the gate, just for your information. So we need to talk about decoding now. And in the next diagram I'm going to show you, I have conceptualized this driver circuit as just a simple square. So let's go to that. So this square right here is one of those bar drivers. I have a digital input here on this side of the square, and then what's marked H1 through 4. These are the bar voltages. They go to the bars. So as mentioned earlier in the decoding scheme, all I need are simple 2-bit to 4-line decoders or a 3-bit to 8-line decoder. Bit A2 is a little different. So what I've got showing here is just the 3 least significant bits. And let's look at our simulation panel. What I'm essentially doing on this, the bottom 2 panels, are my least significant bits A0 and A1, and we're just letting that count binary. This is showing our quiescent point status. So if Q point is high, what's going on is we're allowed to decode this address set by A0 and A1. So you see that the bar that is at 0 volts increments over, and only that one bar of H1 through 4 is at 0 volts, and any other time all the other 3 are at minus 250. Now, whenever the status Q point goes low or 0, all bars are going to be at 0 volts. That's our idle point. We need this idle current going on. And I have one other item here to discuss, the select option. I need to be able to turn off or deselect all bars, make them all minus 250 volts. This should say minus 250 volts. So I need this other option, the select status, if you will. During the write process, I need to be able to turn off the 1 bit that I had selected already during the write process. I need to turn that off if I'm writing a low to that bit. So in other words, if this select goes high, all bars will be at minus 250 volts. There's absolutely no current getting through any window. On the other hand, if I have a low here, the selection process can happen. And really all I'm doing is I'm just using the enable pin of these 2-bit to 4-line decoders. The A2 bit is a little different. Essentially what I have here is a 1-bit to 2-line decoder with the same sort of gating involved. The other more significant bits, I've got another 2-bit to 4-line decoder for the V group 1 through 4, and then I've got a 3-bit to 8-line decoder for the H prime group. But conceptually it's all the same as this. Let's have a look at the selector bar driver boards. Each card that we see here, each one has 4 drivers on it, so I grouped them sort of naturally with the way the tube presents itself. So this first grouping of 4 is the H group, H1, 2, 3, and 4. I'll go to the back. These 2 are for the H prime group, H prime 1 through 8. This is the V group, V1, 2, 3, and 4. And then finally, this card right here, which is only half populated, is the V prime group, V prime 1 and 2. So returning to the front here, this is the plus minus 12 volts for the transistor side of the opto isolator. Here's our digital input, our output going to the selector bars. I also have my minus 250 volts here, so I'm trying to be careful not to touch this thing. So I have my microprocessor stepping through what it was doing for the introductory sequence. And all I'm going to do is just kind of show you some timing signals right here. Channel 2 is the digital input. Channel 1 will be the selector bar voltage. And we're going to come around to the oscilloscope and have a look at these signals. So we see here on channel 2, this is our digital input from the decoder. It's a nice square pulse. Looks like I'm going for about 150 microseconds on this. The yellow curve is the voltage to the selector bar. I just picked a selector bar at random, but you can kind of see a little RC charging curve here at the front end of this thing, and that's kind of to be expected. The capacitance of any one of these bars to any other part of the circuit is nominally 20 picofarads. According to the data sheet, according to the patent information, of course, I'm driving this with a MOSFET and a 100k ohm resistor, so the effective resistance will depend on whether I'm in the on or off state, but the longest time would be a time period of 2 microseconds, and that old adage that everything's over after 5 time constants. So 10 microseconds would be sort of what I would expect for a curve, and if I look at this, looks like it's about over after about maybe 20. No, that's about 50 microseconds, so maybe the capacitance is a little higher. The shutoff is much sharper because I'm shutting it off, returning this to ground by turning on that MOSFET transistor. So there we have our selector bar drivers and decoders, sort of in a nutshell. So this is our decoder driver setup for the selection bars, how we do this. That's it for video 2. So thanks for playing along.